All right, hello, lovely humans. Thank you so much for working through this series on area. This is my favorite part, and I hope that you will agree that it is almost magical. So, calculus can be an intimidating subject, and I think a lot of that is because when we're taught all of these new symbols, it isn't always clear what we're doing. And so in a discussion about area, it's like, well, that's just integral calculus. So let's pull a complex topic and make it tangible. So even if you can't do calculus, if you've never taken calculus, bear with me, because if you can do area and you understand graphing, you can handle integrals. I promise. Okay, so let's start simple. So we are going to work with a example that is straightforward that we have already talked about. A triangle. The lovely triangle. Okay, so in this case, you have bared with me as I have refused to use actual numbers and instead give you variables. I love variables because it means you can apply the equation to any circumstance that is appropriate. But since this is a new example, let's put some numbers to this. So first of all, I'm going to label my axes because that's appropriate in mathematics. And then I'm going to say I have a triangle with length 5 and height 3. Okay. And it sits at 0, 0. So then I know that this point is 5, 0, where this is x, y, and this point is 5, 3. Okay, so this is helpful because we need to know what the equation of this line is. So for a moment, let's ignore the fact that we have a triangle. Okay, well, if we just look at this line, then we know that y, the equation of a line, the generic equation of a line, is mx plus b, where m is our slope and b is the point on the y-axis that our line intercepts. So in this case, b is 0 because our line goes through 0, 0. Cool. All right. If our triangle was situated up here, then we could do the exact same thing, but b would be a different value. We'll keep it simple for now and say y just equals m times x. And now we're like, oh, but wait, what is m? I thought you said we were using numbers. Haha, yes. So in this case, the slope is rise over run, or rise over run, or I guess in this case I could go like that. Rise is 3, and run is 5. So y equals 3/5 x. And that is the equation of this line. Y equals 3/5 x. Cool. Okay, so now we know, and this is kind of a given, so take this with a grain of salt, the area under this line equals the integral of our function with respect to x times dx. And you're like, wait, what? Where the heck is this coming from? How did you get there? No. I know, right? It's always annoying when when the equation is presented without any explanation. So let's back up a second. This is our equation. Where does it come from? So remember how in part 1, it might be a distant past, but in part 1, we took a rectangle and we said, okay, if we have a length of b and a height of a, if I want to figure out the equation for this rectangle, I break it into smaller chunks with width 1, and I add them up until I get to the end. So that's what we're doing here. Dx basically just means a tiny little chunk of x. So this is a little chunk of x, this is a little chunk of x, this. We're doing the exact same thing. So in this case, the width of each of these chunks is dx. That's it. That's what this means. So that is this piece. And this piece is basically the height of our function. So in that case, it is this equation right here. Because this is basically telling us, well, the integral of f of x is telling us how much it is changing. Okay, so this piece gets us the width, and this piece gets us the height. Oh, okay, so another way to think about it is, like, it clicks for my head, so now I can share that click with y'all. So at any given point on this line, we plug in a value for x, right? And that is where we get the value for y. So literally, these points, as we're changing, so if we were to plug in 5 for x, we would get 3 for y. Same thing here. If we plug in 3 for x, we would calculate the value for y, and that is the height. That's it. So this equation represents the width, dx, times the height, which is just y. So another way to write this would be y, where y equals 3/5 x. We like to write a function of x because we recognize that if we're going to take the integral, we need to have x in our integral. In other words, we need to write our equation in terms of the variable that we are integrating over. So in this case, that would be x. But that is cool because we already did the hard work there. We know that y equals 3/5 x. Boom. So that is the equation for our area. And since we have a bounded curve, which means that we have a starting point of 0 and an ending point of 5, we put the start and end point on our integral so that we know where to go. Pretty straightforward. It's kind of like that summation sign that we've talked about before. Okay, so now this is where the calculus bit comes in, and unfortunately there is a little bit of memorization, but it really just has to do with understanding how integrals work. And an integral is the opposite of a derivative in much the same way that multiplication is the opposite of division, or vice versa. Division is the opposite of multiplication. So in this case, to kind of reverse a derivative, we are going backwards, and so we will get 3/5 times 1/2 x squared. And normally we would add a constant for due diligence because the derivative of a constant is 0. So if you have an integral that looks like this, you might have a constant that was hiding out. But since we have a bounded curve, we don't need to worry about that. And so we go from our starting point to our ending point. Okay, and so now we have the area of our triangle equals 3/5 times 1/2 x from 0 to 5. So we start, it is final minus initial, where this is our final and this is our initial starting point. Fortunately, 0 times 0, if we plug in 0 for x, 0 squared is 0, that equals all 0. And so we have our 5 minus 0, so we get 5 squared minus 0, and that just equals 3/5 times 5 times 5. That 5 cancels, and we just get, oops, I dropped my 1/2. Haha, I was like, something's wrong here. 1/2 times, there we go, half times 3/5. So now we get 1/2 times 3 times 5. Oh, look at that! That's the equation of a triangle. 1/2 base, 5 times height, 3. Done. Pretty rad, huh? So that is where calculus comes into finding areas of different shapes. And so what is super, super cool is that we actually can do this for any curve. So say, for example, we had a parabola where y equals x squared, and I wanted to do the same thing, find this area at 5. So I could do the exact same thing to find this area. The equation would be from 0 to 5. My starting point is here, my ending point is here. We add up little chunks of dx times the height, which is just going to be x squared, and we do the same thing. So in this case, I get 1/3 x cubed from 0 to 5. I'm going to do this over here, 1/3 times 5 cubed equals, what is this, 125 over 3. There you go. So now all of a sudden, this shape, which I wouldn't be able to break into smaller chunks without calculus, or it would take me a long time because I'd have to draw it to scale, maybe cut out some chunks, measure and multiply and do way too much work. Calculus makes it a breeze. So that's why calculus is awesome. It is a super handy tool. Okay, please let me know if you have any questions about this. I did kind of gloss over how to do an integral. Happy to cover that if y'all are interested. I am pretty much wrapping up Algebra 2 and algebra in general, and so personally I would love to go into calculus, but I can also tackle some other topics in physics or math or other types of sciences, statistics perhaps. Let me know what you're interested in and we'll tackle it together. All right, thanks very much for watching and we'll see you next time. Bye!